Hello everyone. Today we are going to understand one of the most powerful ideas in probability, Bayes' theorem. This theorem helps us answer a very important question. How should we change our belief when new information is given? To understand this, let us begin with a real life situation. Suppose there is a rare disease that affects only 1 out of 100 people, that is 1% of the population. Now, there is a medical test for this disease. If a person has the disease, the test correctly shows positive 90% of the time. It means, suppose there are 100 people who are having the disease and they take the test. The test says 90 people are having the disease. If a person does not have the disease, the test correctly shows negative 95% of the time. It means if there are 100 people and they take the test says 95 people are not having the disease. Now, imagine this situation. You take the test and the test result comes back positive. Now comes the important question. What is the chance that you actually have the disease? Is it 90%, around 50%, or something entirely different? Since the test identifies 90 out of 100 of those who are having disease and correctly identifies 95 out of 100 for those who are not having disease, most people immediately say 90%. But that answer is wrong. The correct answer is only about 15.3%. To understand why this happens, we need Bayes' theorem. At the end of the video, we will solve this problem. Before we solve the medical test problem mathematically, let us understand the idea using a much simpler example. Suppose you are blindfolded. There are two boxes in front of you. Each box consists of 10 balls, and color of the ball is either blue or red. You need to randomly choose one box, and from that box you need to pick one ball. Your blindfold is removed now and informed that the color of the ball that you picked is red. And when I ask the question, what is the probability that you pulled this red ball from box 1? To answer this, we need to revisit our thoughts during the entire scenario. Consider again the scene when you are blindfolded. Before you even reached out and picked the ball, your belief was perfectly balanced. You had no information to prefer one box over the other. So your assumption was probability of box 1 equal to 0.5 and probability of box 2 is equal to 0.5. This initial belief before seeing any data is called the prior probability. It represents what you believe before evidence enters the picture. Now, you remove the blindfold. You saw the color of the ball is red. This observed fact is called the evidence. Evidence is the new information that forces us to reconsider our initial belief. Now comes the most important step. You look inside the boxes and ask, if the ball came from box 1, how likely is a red ball? As we can see, there are 3 red balls out of total 10 balls, so it is 3 by 10. Similarly, if the ball came from box 2, how likely is a red ball? So it is 6 by 10. Clearly, box 2 produces red balls much more frequently than box 1. This comparison answers the question, how probable is the evidence assuming a particular hypothesis, here boxes, was chosen? This quantity is called the likelihood. The greater the likelihood, the stronger the evidence in favor of that hypothesis. Here hypothesis means choosing the boxes. After reaching this stage, your initial beliefs or prior probabilities of two hypotheses, that is, probability of box 1 and probability of box 2 is no longer 0.5 each. We want to update our beliefs by considering the evidence that the color of the ball is red. We need to find out these values. Probability of box 1 given the color of the ball is red and probability of box 2 given the color of the ball is red. These probability values are known as the posterior probabilities. Posterior probability is the updated probability of a hypothesis after taking new evidence into account. The whole idea of the Bayes theorem is finding out these posterior probabilities. Now we combine everything. Bayes theorem systematically updates our initial 50-50 chances of each boxes, that is prior probabilities, using how strongly the red ball supports each box. So initially, we believed that we have a 50-50 chance for each box. Later, we saw the red color ball and we look into the each box and find out that box 2 is having more red color balls. Now, we think that box 2 is having more chance and box 1 is having less chance. Now, we will calculate these values. The formula of the Bayes theorem is given as probability of A given B is equal to probability of B given A multiplied by probability of A whole divided by the probability of B. In our example, A is the event of choosing the box 1 and B is the seeing the red colored ball. So our formula becomes probability of box 1 given red colored ball is equal to probability of seeing red color ball when you are in the box 1 multiplied by probability of box 1 whole divided by the probability of getting the red colored ball. So here probability of A is known as the prior probability. It means like probability of box 1. It is known as prior probability. Probability of getting red colored ball. It is the evidence. And probability of B by A. It means probability of red color ball when you are in the box 1. It is a likelihood and it is known as the posterior probability. So as a whole, we can write it as posterior probability is equal to likelihood into prior probability whole divided by the evidence. Let us look into the question. Box 1 contains 3 red balls and 7 blue balls. Box 2 contains 6 red balls and 4 blue balls. A box is selected at random and then one ball is drawn from the selected box. It is observed that the ball drawn is red. Find the probability that the ball was drawn from box 1. We will solve this problem by tree method. First, draw an initial node as a starting point. We are having two boxes, so draw two nodes and paths that connects the starting node. On these paths, we represent the probability values of reaching these nodes. So, for two boxes, the chances are 50-50. So, probability values are half each. Now, consider the box 1. We have two possibilities of getting a ball. Either we can get red colored ball or blue colored ball. Probability of red color ball when we are in the box 1 is 3 by 10. Similarly, probability of blue colored ball when we are in the box 1 is 7 by 10. Now, repeat the same for box 2. The probability of getting red color ball when we are in the box 2 is 6 by 10 and probability of blue colored ball when we are in the box 2 is 4 by 10. But we are interested only in getting the red colored ball. So, we will erase the paths that connects the blue colored balls. As we can see, there are two paths that gives the red colored ball. It is the path 1 and it is the path 2. So we can write probability of red colored ball is equal to, by following the path 1, we will get the value 1 by 2 multiplied by 3 by 10 plus, by following the path 2, we will get the value of 1 by 2 multiplied by 6 by 10. But we need to calculate probability of box 1 given it is a red colored ball. By following the Bayes theorem formula, we can write it as is equal to probability of red colored ball when we are in the box 1 multiplied by probability of box 1 divided by probability of red. As we can observe, the numerator part is nothing but the path 1. So, when we substitute the values 1 by 2 multiplied by 3 by 10 divided by the 1 by 2 into 3 by 10 plus 1 by 2 into 6 by 10. So, when we calculate this, we will end up with 3 by 9, which is 1 by 3, which is equal to 0.33. So, the probability of box 1 when we observe the red colored ball is equal to 1 by 3. So we updated our box 1 probability. It is the posterior probability of the box 1. In a similar way, the probability of box 2 given the red colored bar is 2 by 3, which is nothing but 0.67, and this value is 0.33. So these are not anymore 0.5% each. So these are updated values. So it is the example of an Bayes theorem. Let's look into the one more example. There are 3 machines ABC in a factory, and these 3 machines manufacture the same type of item. Mission A produces 25% of the total items, Mission B produces 35% of the total items, and Mission C produces 40% of the total items. And these missions also produces defectives also. So the defective rates are given as 5% for mission A and 3% for mission B and 1% for mission C. Now, an item is selected at random from the total production and is found to be defective. Find the probability that the defective item was produced by mission C. We will solve this problem by tree method. We will start with an initial node. Since we are having 3 missions, we will draw 3 nodes and connect them from the starting node. Since A produces 25% of the total items, the value on the path becomes 0.25. Similarly, for B, the value is 0.35 and for C, it is 0.40. Now, we will move to the mission A. It can produce defective items as well as non-defective items. Since the defective rate is given as 5%, the value on the path becomes 0.05. For non-defective, it will become 0.95. Similarly, for mission B, the defective rate is 3%. It means the value is 0.03. And for non-defective, it is 1 minus 0.03, which is nothing but 0.97. Similarly, for mission C, the values are 0.01 and 0.99. Since we are interested only in the defective items, we will erase the paths that connects the non-defective item. As we can observe, there are 3 paths that gives us the defective items. This is the path 1 and this is the path 2 and this is the path 3. The question here is probability of getting selected item is coming from mission C given that item is defective. We can write it as probability of C given D equal to path 3 divided by the total path. So for path 3, the value is 0.40 multiplied by 0.01 whole divided by the total of each and every path, which means 0.25 multiplied by 0.05 for the path 1 plus 0.35 multiplied by 0.03 for path 2 and plus 0.40 into 0.01. So when you calculate this, we will get the value approximately it is 0.148. It is the updated probability of mission C by considering the defective item evidence. Now, we return to the medical question that we discussed at the start of the video. Again by tree method, we will start with an initial node. Now, we have 2 possibilities. Either we have a disease or not having a disease. In the question, it is given that prevalence equal to 1%, which means chance of having disease equal to 0.01. So the chance of not having disease equal to 1 minus 0.01, which is equal to 0.99. Now coming to the test results for the persons who are having disease. The test can give either positive or negative. In the question, it was given that the test correctly gives a positive result 90% for those who are having disease. So the value becomes 0.90 for the positive. For the negative, the value becomes 1 minus 0.9, which is equal to 0.1. Now, we will move to the persons who are not having disease and observe the test results probabilities. Since the test correctly identifies negative 95%, the value becomes 0.95, and for positive, the value is 1 minus 0.95, which is equal to 0.05. And the question is, if the test result is found to be positive, find the probability that the person actually has the disease. Since we are interested only in the positives, we will arrange the paths that connect to the negative test results. Now, we need to find the probability of the person actually has the disease given the test result is positive. As we can observe, there are two paths that gives the positive result. This is the path 1 and this is the path 2. Since it is asking disease and positive, it is nothing but path 1 divided by the total path. And when we substitute the values, it is 0.01 multiplied by 0.9 divided by 0.01 multiplied by 0.9 plus 0.99 into 0.05. After calculating, we will get the answer. It is 0.1538. Even though the test is accurate, the disease itself is very rare. So that's why the final probability is only about 15.3%. So Bayes theorem teaches us a very important lesson. Test accuracy is not the same as probability of the disease. Rare events stay rare even with good tests. We must always consider prior probability. Bayes theorem is simply a logical way to update beliefs when new evidence appears. Thank you.